Thanks everybody to be here. Welcome to the session of Sub-Riemannian geometry and neuromathematics. It's my pleasure to introduce the first speaker, who is Giovanna Citti. She's a mathematician. She's from the University of Bologna and USS of Paris. And from the 1st November of this year, she will be a member of the Accademia dei Lincei of Rome. She one of the founder of the field of neurogeometry, neuromathematics, and the last year she was invited at the Field Institute of Toronto just to introduce this field at international level. Donc, then she's going to talk about submanifolds of fixed degree in graded manifolds for perceptual completion.
I thank very much the organizer for giving me the opportunity of presenting this work, which is joint work.
Yeah.
Oh yeah, you don't have a matter.
Sì, puoi toglierti la maschera.
Get off the mask. I have mine.
No, è qua il microfono.
È il metro che manca. Oh, okay.
Yeah, maybe a distancing. She's asking.
I'm vaccinated. I would like to thank the organizer for giving me the opportunity of presenting these results, which are joint results with Giovannardi, Alessandro Sarti, and Manuel Ritoré. I present a model of perception completion expressed as sub-Riemannian minimal surface, joint work with Alessandro Sarti, and I will show that adding more feature, we have to consider surfaces of higher codimension. For this kind of surfaces, it was not clear which is the notion of curvature and a minimal surface, which has been developed with Giovannardi and Ritoré. And then with this notion, we provide a new model of completion, which depends on orientation and curve. Here on the left, you see the famous Cannes triangle. We see a triangle which is more wide than the background and which is perceived as if it was above the background, but its boundaries are not present as gradient of the image. And this is why these boundaries are called subjective boundaries. They are produced by the visual system. And here we have a schematic representation of the visual system. The visual signal arrived on the retina. And then here on the back, we have the primary visual cortex, whose receptive profiles, together with the optical nerve, receive input from the retina. And then the signal is processed within the family of cells in the primary visual cortex. The first description of the brain are due to Hubel and Wieser, and the first model to Hoffman, Petitot, and Tondu. In a seminal paper in 1999, Petitot and Tondu described the visual cortex as a fiber bundle and modeled the emergence of subjective contours as minima of a constraint general functional. In 2003, he recognized that minimal were geodesic in a sub-Riemannian metric, and in the same year, we, together with Sarti, introduced a new approach based on sub-Riemannian minimal surfaces, which allows to work on the whole image, and it is no more necessary to study geodesics, which are single curve in the image. In a series of papers, we proposed a model in which each set of cells is modeled in group. Action of the cell receptive profiles for input from retina is modeled as a sub-bundle, as the selection of a sub-bundle of the tangent bundle with the sub-Riemannian metric. Within each family of cells, there is a long-range connectivity, which is modeled as propagation in sub-Riemannian metric. And here we have a first model in which we consider only simple cells sensible to position and orientation. The set of cells is obtained from a fixed one, say this one, from translation, you see here, and rotation. And so this is a group of translation and rotation. In presence of a visual system, the input, the whole hypercolumn over one point, so this is a column over this radial point, fires. The higher answer is provided by the size sensible to orientation of the boundary. And so this level line, see this blue one, is lifted to a new curve, integral curves of two vector fields, which are represented here, x1, cosine theta dx plus sine theta dy, and the theta. This means that a subbundle of the tangent bundle is defined as the span of these two vector fields. These vector fields, together with their commutator, are linearly independent, which means that the Hermite condition is satisfied, and the result of PDE are well known and can be applied. So each level line is lifted to a curve, and the whole image is lifted to a function. If a part of the image is missed, it is completed by a two-step algorithm. First, propagation along the conductivity is represented as a heat equation, and then the subtraction of maxima recovers the surface. And if you first diffuse and then suppress the orthogonal component, you just obtain a tangential diffusion, which induces a motion by curvature. And in this way, when t goes to infinity, the surface is completed as a minimal surface. If we select true feature, we obtain a two codimensional graph. And so we cannot directly repeat this construction because in codimension 1, there is a large literature, which I briefly record here. But in high codimension, we only have the notion of area and no notion of first variation is known. Something is known only for curves, as there are the famous results of Montgomery about geodesics and abnormal geodesic. We will see that in this paper, while studying higher codimension, for the first time we recognize that a similar phenomena can also present for surfaces. So let's recall what is a graded structure is a smooth manifold N with a metric G, whose tangential space can be organized, represented as direct sum of vector space at every point, so K1 of P, direct sum of K2 of P, and so on and so forth. If a vector fields belong to Ki and Y belong to Kj, then the bracket belongs to Ki plus j. The homogeneous dimension is the sum in I of the dimension of one of this times I, and then you sum in I. I will here impose the additional requirement that the dimension of KEIP is constant, which is not necessary, but will simplify the presentation. And I call degree of V equal I if a tangent vector V belongs to the I element of this decomposition. The notion of degree can be extended from vector to M vector. So if M vector xj is represented as xj1 wedge xjm, then its degree is the sum of the degree of vector field which compose it. And then we can also define a basis adapted to the graded manifold, meaning that first we consider a basis of the first layer, K1P, and then we complete it to a basis of the direct sum of K1 and K2, and so on and so forth. One defines the degree of the whole manifold, we define the degree of a submanifold. So we consider a submanifold M with a parameterization phi, and a metric defined on the domain of the parameterization. This submanifold inherited a graded structure simply called the K tilde I at the point P, is the intersection of the tangent plane to M at the point P with Ki of P. The degree of the manifold will be defined exactly as before, as the sum at the point P of the dimension of K tilde IP multiplied by I. In this case, it is not possible to make the same simplified assumption that this is constant, and we need to define the degree of the manifold as the maximum of this degree. The area of a manifold dimension and degree d is given by the integral of the projection of the vector E1, Em on the set of M vector of dimension d, and then we integrate in with respect to the measure. E1, Em will be a M orthogonal basis of the tangent space. Now, you see that this definition depends on the degree of the manifold. So this means that when we make a variation in order to introduce the notion of curvature, we have to fix the degree. And so we call admissible variation of a manifold with a parameterization phi a smooth map defined on the domain of parameterization across an interval neighborhood of 0 with value in M, and called gamma of S, with S in this minus epsilon, the function with which depends only on the point in M bar. Now, we require that this variation at the very beginning at 0 is the given parameterization. At every instant of time, it has the same degree of our manifold, and outside a compact set is just the manifold. So just we consider a variation. Now, if we cannot find an admissible variation, we cannot speak about curvature, and we will not be able to give a notion of curvature with a variation instrument, and this is already known for geodesics. Indeed, Montgomery introduced the notion of abnormal geodesics, which are geodesics isolated. Now, we can take the derivative of this variation with respect to the variable S and obtain the variation vector. This cannot have tangent component because tangent component does not change the shape, but only the parameterization of the surface. So we can take a basis, which is the first element, which are tangent, the element of the orthogonal, which has degree bigger than the first element, and then we complete with all the elements with higher degree. So the vector has no tangent components and has components of low degree, which are called H, and components with higher degree. Being a variation vector field induce a differential constraint for first order system on the component H and Y of our W vector, which is called admissible system. And the question is, if a vector field satisfies this system, does it come from a variation? Now, again, the answer is known only for curves, and we have studied the corresponding problem for surfaces, and we introduce a simplified assumption that this metric here has full rank, and if this happens, then at a point, then there exists a neighborhood of this point such that every admissible vector is integrable, so it comes from a variation. And so with this assumption, we can characterize variations. And this, we have applied this to the Engel type structure. Engel type structure is defined as R2 cross S1 cross R, and in this structure we have an orthogonal basis, which I described here. So we choose two vector fields, x1 and x2, and the x2 of degree 1. x1 is cos theta the x plus sine theta the y plus k the theta. So it's the previous one which has been extended. And then another one is the derivative with respect of k. If we compute the bracket is minus the derivative with respect of theta, and so this vector has degree 2. And if we compute another bracket, we find minus sine theta the x plus cos theta the y, so this has degree 3. Now, we consider a manifold as the one which comes from the model, so which is the selection of orientation and curvature. And then we impose a constraint, which is natural in this context because the derivative with respect of x1 of theta is the curvature, because it's the derivative of the arc length of the projected cubic curve. And with our notation, the area, the fourth degree area, has exactly this familiar expression for the area of a graph. We see that you can write explicitly the admissible system in this case, and this ensures that every admissible vector is integrable, which implies that minimal services can be obtained by variational methods. We compute the Euler-Lagrange functional, and here we have a first result in which we complete missing surfaces with this method. So I thank you for your attention.
Thanks, Giovanna, for this short and beautiful talk. And thanks for the accurate historical reconstruction that is not given, citing also the papers, because it's fundamental in a historical reconstruction, citing exactly the papers and for right scientific history. Questions?
Yes, so first of all, thank you for the very nice talk. It was very clear. I have two questions. One more algebraic, the other more practical. So the algebraic one is that when you do this graded decomposition of the tangent, right? If your manifold is a group, and often this is sometimes it depends, could be the case. Is this grading induced by maybe a grading of the Lie algebra?
Yeah, of course.
The second question is, when you said we complete and you show us pictures, what at the end you show the pictures of completion, right? Which type of software, which type of method did you use?
Okay,
Two questions.
Okay.
Yes.
Yeah, the answer is yes. If we have something which is a group, this, for example, is an Engel group, we consider vector fields which are left invariant with respect of the action. This, yeah. And of course, using left invariant vector fields must simplify the implementation, because if we want to use directly the two-step algorithm, we have to first to use a diffusion and then concentrate. And we can use, for example, a kernel, and then we just move through the group action, and we don't have to compute the same at every point. And then here we just use MATLAB.
Oh, MATLAB.
Yeah.
Okay. And in your paper, you put the software, just to see, I was curious.
We just make a very...
Okay.
One more question?
I have a question regarding other type of big groups and graded structures. So you use the Engel group, and I see this connection of iteration, curvature, and this grading in that sense. I was wondering if you have examples of other groups, maybe in public scale or...
Yes, we have a paper together with Petitot, which is on position, orientation, and scale. We have another paper together, couple of paper together with Cocci, Sarti, and myself, another with Barbieri, Cocci, Sarti, and myself on movement. So there we consider the Galilean group and the subgroup of this, which contains the variables of position, velocity, and times, and also the orientation. And then we have now we are developing with Virginia and Caterina, we are developing a stereo model. So we are consider the two projections, the eyes, and then consider the group, which consider these together. And finally, we are extending this method also for other region of the brain. Together with Caterina, we are working on the motor cortex. And the motor cortex has a implementation similar to the visual one, because after that you have the visual motor area. So they have to express in the same way the two types of inputs in order to work in with them together.
Okay. Okay. Thank you very much again, Giovanna.